All right. Oh, lest I forget, let me hand out the attendance sheet. There you go. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class, this opportunity we just have to meet and study linear algebra together. Just help us to glorify you what we do, Lord, this day. In your name I pray, Lord Jesus. Amen. All right, so we started talking about linear transformations. And I started explaining to you, like, one of the beauties of linear transformations is that linear transformations so this time we're going to talk about surjective, injective, bijective. So in the parlance of earlier mathematics, this would be sometimes called onto, and this would sometimes be called one-to-one. And bijective means, let's just say it this way, it has an inverse. Has an inverse function. And so we'd like to understand more about linear transformations. Like last time, I hope I convinced you guys that linear transformations take lines to lines, right? But they do more than that. All right. So let's give a definition, something a little bit bigger, just for the sake of our discussion today. If, let's say, v1, v2, vk, subset of Rn is a linearly independent set, then W equals to the span of all these guys. All right. What's the span? Remember, the span is this. It's the sum I equals 1 to k of c sub I, v sub I, such that, c sub I is an element of the reals for I equals to 1 to all the way out to k. So so that would be a what is this? What is this then? This is a k-dimensional subspace of Rn. All right. And P plus W, which would be things of the form P plus the sum over Ci Vi, I equals 1 to k. All right. Again, here, Ci in the reals, and P a particular n vector is a k-dimensional affine space. Or you could also call it a linear manifold with quote-unquote directing space W. Now, I don't think I even have this language in your homework, but it's something that's probably missing from my current set of notes, and it needs to be, really should be added, honestly. Just so we have a concise and coherent language to talk about these things, because they're really what are of interest. So, I already talked about this idea last class. Can you interpret for me, what would it mean if we had a one-dimensional, what would a one-dimensional subspace of Rn be? You'd have W what? W is equal to like the span of just one thing, right? What is that? That's literally like t times v1 such that t is a real number. What is that? This is a line, right? It's a line through the origin with direction vector v1. All right? What would p plus w in this case be? It's still what? This is in my notation last class. I think I called this what? L. It was like L. I can't remember what I had put p first and v second for the the line with base point p and direction vector v. Is that right? It's 50-50. I did that last time. I don't remember. Okay. I haven't reviewed the tape to remember what I do. I did VP. Ah, rats. So I try to at least be consistent in my notation in one semester. There we go. But that's a line, right? How about k equals to 2? What do you got? Excuse me. You'd have W is the span of two things, right? What are those two things? Well, something like SV1 plus TV2, such that S and T are real numbers, right? Or perhaps I could use U. Well, see, U and V look too much like my V's. I'll keep with the S and the T. And then P plus W. I don't have a name for it, but it's the plane with base point P and tangent vectors V1 and V2. Right, so I could draw a picture. So W would be something like, it goes through the origin. It could be something like this. So here's like your V1, here's your V2, and in this plane W, arbitrary linear combinations of those fill out the plane, right? On the other hand, P plus W, it's kind of a more exciting, you be quiet, something like this. So here's my base point maybe here, here. My point P to start out the plane, right? And to get to an arbitrary point on the plane, I go like, S copies of V1 over to here, and then like T copies of V2 over there to get my arbitrary point on the plane. P plus SV1 plus TV2, right? So in this context, if you think back to your experience with Calc 3, which I think most of you have had, and if you haven't, my apologies. Because I know Calc 3 is not a prerequisite, but by golly, if you guys have had it, I should be talking about it so you can learn, I think professors sometimes operate in this spirit of fear of lack of prerequisites too much. You really should like for your math classes to be connected, And when we have some missing prerequisite because of bookkeeping, we shouldn't let that get in the way of learning. So anyway, this is my ninja way. But basically, the parameters serve as coordinates, right? The parameters serve as the coordinates on the plane. So in Calc 3, we talked about the parameterization of a plane, right? The weights in these linear combinations served as the parameters, essentially, right? What happens if k equals 3? What are we talking about? You're talking about like a volume, right? A three-dimensional space, right? And so if it's in R3, then it's just everything, right? But if it's in R4, there could be more than the three-dimensional space, right? So generically speaking, this is the kind of space that a linear transformation preserves, all right? Like the generalization of what we did last time is that a linear transformation will take a k-dimensional space to a k-dimensional space, all right? Where by k-dimensional space, I just mean a so-called linear manifold, which is, just a fancy way of talking about a plane which is possibly shifted off the origin. But it could be more than a plane. It could be a volume. It could be a hypervolume, right? Be things I can't picture directly. Any questions? So if we, look at the simple calculations, let T be a mapping from, say, Rn to Rm, and let W equals to P plus the span of, V1, V2, Vk. And for the sake of specificity, I'm assuming that these are linearly independent. All right. What can we say about T of W? What does T of W look like? T of W, the image of W under T, would be something like T of what? Well, a typical element of it would be like what? T of P plus the sum, right? I equals 1 to K of Ci Vi. Again here, Ci are real numbers, and P is in Rn. All right. So let's do the math. Linear transformation. So I'm assuming this is a linear transformation. If it's a linear transformation, we can do what? We can break up across sums, and we can pull out constants. So what do we have? We've got T of P, right, plus the sum over I equals 1 to K of Ci T of Vi. All right? But what's that? If you tilt your head and squint, you should be able to see that this is nothing more than like the specific vector T of P plus the span of what? We're not taking a linear combination of Vi anymore. What are we doing? We're taking a sum of these guys, right? So it's literally the span of T of V1, T of V2, T of Vk, right? So this is, what is this? This is again a linear manifold, right? In a fine space. What's the base point? So let's just say this is a linear space. We could say that. A linear space, right? Base point T of P, right? And, T of W is its directing space. Now, what is T of W? So T of W, I'm suggesting, is the span that's, like T of W is literally this thing right here, okay? Oh, my bad, I've used W in a different sense. Let me fix this. Let's call this thing W sub P, just to make a distinction. Watch for this, guys. I'm putting a P here, and I'm putting a P here, all right? So this right here is what I'm going to call W for the sake of this current discussion, okay? Just that piece. The subspace, the part that goes through the origin, not the shifted part. So my question to you, all right, is what's the deal with this linear space now? Like, is it a k-dimensional space? What do you think? Let's look at a specific example. We could have, W could be, say, the span of 1, 1, 1 and minus 1, 1, 0. And we could let P equals to, like, I don't know, 1, 2, 3. And let's let our linear transformation T of x, y, z equal to let us say, we'll put the matrix, I need a 3 by 2, right? No, I'm gonna, well, that's the thing, is there's lots of different things we could do here. The domain has to be, I'm gonna make it go through, I'm gonna make it a 3 by 3. All right, so let us say 0, 1, minus 1, and then 1, 0, 0, and 0, 1, 0. That's a relatively simple matrix for the standard matrix here. So there's your formula. This, if remember, like we talked about last time, if the formula can be written as a matrix multiplication, it is indeed a linear transformation. So for this particular example, what's the situation? Let's figure it out. We've got T of P is what? We got what? 2 minus 3 is minus 1, and 1, and 2. All right, so there's their T of P. What is T of, let's give these things some names so that I don't have to keep writing. Let's do some name calling. This V1, this we'll let V be 2, okay? So what's T of V1? What is T of V2? So what's the situation here? What do we got? So we got 0, 1, and 1. And how about T of V2? What do we got? We've got 1, we've got minus 1, and we've got 1. So how do you decide whether two vectors are linearly independent or not? My question to you is T of V1, comma T of V2, is this linearly independent? Should we need to do any calculation for this? We really shouldn't, all right? Simple check. A set of two vectors is linearly independent. It's only linearly independent if one vector is not a not a scalar multiple of the other. It's pretty obvious here, right? As you look at these two, not scalar multiples, right? Can we agree? Do I need to prove that? Can we just agree that that's obvious? I hope. Yeah. So not linear multiples, therefore linearly independent. Therefore, my T of P plus W here is literally equal to minus 1, 1, 2 plus what? Plus the span of this, T of V 0, 1, 1 and 1 minus 1, 1. So in this particular case, it looks to me like what happened? Looks to me like the image under the linear transformation, right? Like the image of T of P, the image of the linear space, namely T of P plus W, is again what? It's again a linear space. What's the dimension? No. So this is the image under T of P plus W. And this right here is, again, a two-dimensional linear space. Notice that the dimension, the base point doesn't count. The counting of dimension just depends on the number of linearly independent vectors in your directing space. Okay? Example 2, perhaps we could have T of, let's see here, x, y, z equal to, let's see here, I'll do something relatively simple, like 1, 1, 1, 1, 1, 0, 1, 0, 0. So there's my matrix. All right. And let me throw in a 6 and a 7 here for good measure. All right. Let's just, for this one, let's study the image. This time, let's let W equal to, say, the span of see here. Oh, see, that's no good. That one's too nice. My bad. Just a second. Let me fix it. 1, 1, 1, 2, 2, 2, and we'll just put 3, 3, 3. There we go. Great. And let's let W this time be. Well, we'll take the same W as last time. All right. Same W, same P. What happens this time? It's the same W and P as in example 1. So what we're trying to do right now, guys, is understand how do linear transformations act on linear spaces? Like, what happens? What's the story? How can we understand it? All right. Once I've done a couple of examples, I'm going to tell you the big theorem, which completely guides our logic, all right? But I want to just do an example or two so that you appreciate the theorem without me just telling it to you. So this one here, again, we need to calculate what's T of P, right? So what's T of 1, 2, 3? What do you got? 1 plus 2 plus 3, which is 6. Then twice that is 12, then 3 times that is 18. There's T of P. What's T of 1, 1, 1? So we got 3, 6, 9, I think. And what's T of minus 1, 1, 0 equal to? Work it out. You got 0. You got yourself a 0. You got yourself a 0. There we go. Okay. Well, this is kind of obvious. So what's T of the directing space this time? Apparently, it is 6, 12, 18 plus what? The span of 3, 6, 9. So what's the deal? What just happened here? Think about it. What happened? This was a 2-dimensional linear space, right? And this over here is a what? Just a 1-dimensional linear space, also known as a line. So we dropped a dimension. How did that happen? When can that happen, right? So this is really one of my fundamental questions that I want to ask today is, when can we anticipate that the linear transformation will not maintain the dimension of the linear space that we're mapping? All right? By the way, one thing I should mention is why aren't we just looking at graphs? Like in pre-calculus and calculus, we just looked at graphs. Why don't we just look at graphs here? What's the problem with that? how many dimensions can you visualize, right? Maybe 3. So that means you can have a total of 3 dimensions between your input and your output space. That means for graphs, we can only do like stuff with maybe like 2 inputs and 1 output, or 1 input and 2 outputs at most. If you've got 2 inputs and 2 outputs, you need a 4-dimensional space to make a graph. So that's why we were drawing pictures like we did last time, where we look at the input space and the output space, and then we study how particular objects are morphed from one space to the other by the transformation. That's how we do things, how we visualize things here. All right, so let me give you the definition. So definition, T going from say Rn to Rm is onto or surjective if T of Rn is equal to Rm. In other words, if the set T of x such that x is in Rn is equal to Rm. That's what it means for it to be onto. It maps to the totality of the space that it's mapping into, all right? That's an onto map. T that goes from Rn to Rm is 1-to-1 or injective if T of x equals to T of y implies x equals to y for all x, or for all possible like x and y in Rn. So anytime you equate a pair of outputs, then the pair of inputs must be in fact the same. So this is onto, this is 1-to-1. Bijective means both 1-to-1 and onto, all right? So if it's bijective, it's both of these. So this means both 1-to-1 and onto. Right? So for linear maps, all right, so like in general, it's a pain for arbitrary functions. So these definitions, I'm assuming both of these here are linear, all right? Linear T, all right, linear transformation. So like the problem of deciding whether or not an arbitrary function is 1-to-1 or onto is a much more difficult task. But to decide whether a linear transformation is 1-to-1 and onto, it's actually very simple because every linear transformation is essentially defined by its matrix. So we can trade these somewhat abstract ideas for concrete matrix calculations, right? So, but I probably should do a little bit, one other sort of abstract thing here, lemma. T, the kernel of T, what's that? Well, that's x in Rn such that T of x is equal to 0, all right? That's the kernel of T. So listen, I mean, like, let me not belabor the point here. This is the same as what? So how can you rewrite T of x equal to 0? It's the standard matrix of T times x equals to 0, right? So can you tell me another name for this set? We already have a name for this set, yeah. Null space, right. This is nothing more than the null space of the standard matrix. So kernel is a concept which is defined for abstract linear transformations. So in particular, it applies to a concrete linear transformation like we're talking about here, T. There's that. But that's not the lemma. The lemma is actually this. T is 1 to 1 only if the null space of T is equal to just the set containing 0. So the proof is really, really simple. So if T is 1 to 1, then T of T of x equals to 0 is equal to T of what? Of course, this is the same as what? Kernel of T being 0, right? Those are one and the same. I'd rather talk about the kernel of T for the sake of this proof because it's like 2 less brackets to write. That's kind of it. I'm mostly joking. So T of x equals to 0. What's 0 equal to? Well, 0 is also T of 0, right? Do you guys agree? 0 maps to 0 for a linear transformation? I don't suppose I proved that in here, but you could prove it pretty easily. And so what does that mean? If T is 1 to 1, you've got T of x is equal to 0, and T of 0 is equal to 0. What's that say x is equal to? If it's 1 to 1. Remember? Outputs being equal means the inputs are the same. So that implies that x is equal to 0. Right? So thus, the kernel of T is equal to 0. So that's this direction of the proof. The other direction, if we have kernel T is equal to 0, right? Suppose T of x equals to T of y. All right, what if T of x is equal to T of y? Well, if T of x is equal to T of y, that tells me that T of x minus T of y is equal to 0, right? Which tells me what? If it's linear, what can we do? T of x minus y. You got it. But if T of x minus y is equal to 0, this means that x minus y, by definition, is an element of the kernel. But the kernel of T is equal to 0 by assumption here, so that implies x is equal to y. Because if x minus y is equal to 0, that forces x to be equal to y. Therefore, a linear transformation is 1 to 1 if and only if it has a kernel which is 0. Or in other words, that the null space is 0. All right? Are we in agreement? Okay. So, let's see here. Be careful. Time flies when you're having fun. Okay, so if here's a similar proposition. If T is 1 to 1 and S equals to, say, v1 vk is a linearly independent subset of, like, the domain of T, then T of S is linearly independent subset of the range of the codomain. Let me just be civilized and say Rn in Rm here. Let's suppose that T is a mapping from Rn to Rm like we've been doing the whole rest of the lecture. So let me stop not doing that. Proposition. So it turns out that if you want to preserve the dimension, of the directing space, if you will, if you had that the mapping is 1-to-1, that would suffice to do it. All right. So like, to prove this proposition, let's see here. Well, I'm not going to prove that proposition in here. That's not what this class is, right? This is actually true, though. If the function's 1-to-1, in other words, if the kernel is 0, it will map a linearly independent set to a linearly independent set. It's actually still true as long as the span of the vectors involved doesn't fall into the kernel of the map. So it's true, a little bit more broad context in this, but anyway, let me get to the point here. So the theorem that we have for today is simply the following. If I can find it. I will find it. It will not hide itself from me. It's a very simple theorem, really. So let me put it up there in the middle, front and center, so we can see it better. Here it is. Theorem 5.3.6, really the main event for today. If we have L, a linear transformation from Rn to Rm linear, then with the usual L of x equal to the standard matrix of L times x, right? Then number 1, L is 1-to-1 if the columns of the standard matrix are linearly independent. And number 2, L is onto, or surjective. That's if and only if. If and only if the columns of the standard matrix span Rm. And we can decide both of those questions, right, by doing what? Like finding the standard matrix, right, and looking at row reduction, right? Because like if the number of pivot columns is the number, we can identify columns being linearly independent if they're all pivots, for example. Like if you go back to example 2, right, now, do you have linearly independent columns? Like let's look at example 2 in a new light. Do we have linearly independent columns? Certainly not, right? What's the deal with that one? Can you tell me what the kernel is? What's the kernel? What's the null space for T? So check this out. The kernel for T is what? It's the null space of, and you can reduce this down to what? 1, 1, 1. It's the same. It's one and the same as that, right? Because that's a row equivalent matrix, and the null space for the matrix and a row equivalent matrix is the same null space. So that's literally what, like x, y, z, such that what? X plus y plus z equals to 0, right? If you like, that's minus y minus z comma y comma z, such that y and z are real numbers. In other words, it's the span of minus 1, 1, 0, minus 1, 0, 1. So here, and this is not an accident, guys, the kernel, or the null space of the matrix, will be a linear subspace of the domain for the function. So this right here, by the way, is a two-dimensional linear space. What was the problem then? What's the range of t? I guess I haven't talked about that yet, but what's the range of t? It's also called the image of t, so that would be like t of, in this case, R3. What's that equal to? It's just equal to what? The span of what? What is t of x, y, z? It is a linear combination of the columns of the matrix, right? But this silly matrix has the same column, all repeated, right? So linear combinations of the columns of that matrix is nothing more than the span of 1, 2, 3. Exceedingly silly. So the range is a one-dimensional space, right? So no matter what you feed this transformation, what it's going to do is it's going to spit out, at most, this one-dimensional space, right? So like, as a follow-up example here, if I was to say, look at W2 equal to, oh, I don't know, say the span of, minus 1, 0, 1, what would have happened? What would be t of W2 in that case? It's the span of t of minus 1, 0, 1. But what is that? T of minus 1, 0, 1 is nothing more than 0, right? And that would be what? Well, just the 0 space, just the origin. Now, so we've seen in my W, my linear space P plus W, and now this line W2, both times we've dropped a dimension, right? The input was one-dimensional, the output was zero-dimensional. The input was two-dimensional, the output was one-dimensional. Does it have to happen? Is there something that this linear transformation won't drop the dimension of? Like, what if we were to look at, can you guys tell me the thing it won't drop the dimension of? What if we look at t of 1, 2, 3? What's it do? Well, that's not the way to think of it. What if we look at the t of 1, 0, 0, what do we get? Well, it's not the only thing, but well, let me just say it this way. If you have v, which is not an element of the kernel of t here, then that means t of v is not equal to 0, right? Thus, if we make W3 equal to, like, say, a point, any point you like, plus the span of such a v, right? Then t of W3, is it that time already? Let's see here, t of p. Actually, what time is that? I don't know. Plus this, plus the span of TV, right? So there is an uber answer. Any of the one-dimensional spaces, right, which I have direction vector not in the kernel, will be mapped to this. And this is what, actually? That has to be the span of the vector 1, 2, 3, actually. So it's kind of boring. All possible lines which don't fall in the kernel, they're mapped to the line with direction vector 1, 2, 3 by this mapping. Okay, so like, I guess I stumbled into today talking to you guys about a slightly more complicated question than I originally intended, which is the question of, for like an arbitrary linear map from Rn to Rm, how can we decide whether or not an arbitrary linear subspace is going to drop dimension under its mapping? The answer is somewhat complicated. Like, it depends on whether or not part of that subspace you're mapping falls inside the kernel of the map or not. If it does, anything's in the kernel gets squashed to 0. So if a piece of your subspace you're mapping has somehow fallen inside the kernel of the map, it can get squished, basically. The one last thing I want to talk to you guys today about is the case of equal dimension. So check this out. If, let's just think about a little parallelepiped like this with sides v1, v2, v3, right? What happens if we, say, feed that under a linear transformation t, and we get an output, right? T of v1, t of v2, and, let's say t of v3. So, as we talked about last time, right? A linear space will get mapped to a linear space. So, like a cuboid will get mapped to a cuboid. What's the relation? What's the relation of the volumes of these? Let's figure that out, and that'll be it for today. So, what's the volume of the input? What's the volume of the, v1, v2, v3 is what? Like plus or minus the determinant of the matrix with those concatenated, right? That would be the volume of this guy. So if I call this P. And so over here, this is T of the parallelepiped, right? What's the volume of, T of P? It would be like plus or minus the determinant of what? T of v1, T of v2, T of v3. Aha! But that is plus or minus the determinant of the standard matrix of T times v1 times the standard matrix of T times v2, standard matrix of T times v3. But what do we know about matrix multiplication? We can factor out the matrix, right? Like that. And then the determinant of the product is the product of the determinants. Therefore, what you got here is plus or minus the determinant of the standard matrix of T is the determinant of the v1, v2, v3. Aha. So we get the following result. The volume of the image of a parallelepiped is equal to plus or minus the determinant of T times the volume of the original parallelepiped. So the determinant of the transformation tells us how the volume of like a unit cube or whatever, unit cube in particular, will rescale. This is exactly why in Calculus 3 you had determinants appearing in your change of variables, because there you're deciding how the product of the differentials, the so-called measure of the integration, changed under a change of variables. And infinitesimally, a change of variables, even when it's nonlinear, can be made linear through something called the Jacobian matrix. And that Jacobian matrix is exactly the matrix that you were taking the determinant of in your change of variables Calculus 3 theorem. I'll try to make that a little bit more explicit in a future lecture, but we don't have time today. So this silly theorem should allow you to solve all of the homework problems pretty much that I've asked you. You can decide whether it's 1-to-1 or onto just using this simple. Because you guys know how to decide these questions by row reduction, right? When are the columns linearly independent? That means every column has to be a pivot column, right? When do they span Rm? That means every row must be a pivot row, right? If you've got one non-pivot row, it means you're missing something in the output. Anyway, thanks guys.